take up today one aspect which was related to the free energy associated with the undercooled melt. We talked earlier that the I, which is the nucleation rate, is basically related to I would say, I will not even put the equation there, is related to delta G star. All of you know the equation, so I will not put the equation. Of course, there is also another term which we always remember, which is the delta G d term, which one has to consider, and delta G star is related to delta G V. Am I right? That expression also many of you know. For a spherical nucleus we can talk about it, and if that is what controls delta G star, for example I can put the equation for this case, let us say 16 pi by 3 gamma cube by delta G V square, let us say. So, that means this controls this, which to a large extent controls this, at least at the temperatures above the nose of the TTT diagram. At all temperatures above the nose, what controls the nucleation rate is only this. Am I right? So, if that is the case, then the nucleation rate to a large extent is dependent on this. And how do I know that value? What is delta G V? Delta G V is the driving force for solidification. If I draw this G versus T, so this is let us say solid, this is let us say liquid, and this is our melting point Tm, and at any temperature below the Tm, T less than the Tm, liquid has a higher free energy than the solid. Am I right? And this difference in the free energy between the liquid and solid, which is what we call it as delta G V, that is our delta G V, and that is what drives the liquid to become a solid. And the higher the undercooling, usually this is higher, as you can see from that curve itself. This 2 start deviating more and more as you approach lower and lower temperatures, and at the Tm the delta G V is 0. That is why in principle at the melting point there is no transformation, you do not have any transformation at all, and you need the liquid to be undercooled. You may say that even for heterogeneous nucleation for that matter, you need a small undercooling, however small that could be. You need a small undercooling for the liquid to transform to a solid. We are not simply talking in terms of the barrier for nucleation. Barrier for nucleation is anyway there, that is the surface energy. I may say that I am providing you the surface energy, why not the transformation occur at the melting point? Because there is because when a surface is already provided, what is the problem? Then we say, if I want the transformation to occur at the melting point, delta G V is 0, and if the delta G V is 0, that there is no driving force at all. So, even if you provide a surface which is a perfect wetting surface, let us say the theta is 0, contact angle is 0, even then you need an undercooling. But usually because such surfaces are not available, you need a higher undercooling, one to give you a driving force, second to take care of the surface energy problem. If you have certain driving force that is available, part of this driving force can be spent to create the surface, so that the surface energy problem can be taken care. So, that is why we always write this expression delta G, which is the overall change in free energy for liquid to solid transformation, is given by 4 third pi r cube into delta G V plus 4 pi r square into gamma. Remember, assuming that gamma is 0, delta G is actually this. So, the driving force for the nucleation for the solid to form, if you assume that there is no surface energy at all, that means there is a perfect nucleating site available and the surface energy is very small. So, even if you assume that, then this is equal to this, and at Tm this is 0. So, this is 0, is not it. So, in principle you need a higher driving force, so that this takes care of the necessary driving force. So, only when delta G, this delta G is negative, the transformation will occur, am I right. So, any transformation for it to occur, the driving force has to be negative. This is the overall driving force which takes care of both surface energy and this, and in these two terms we know pretty well that this is at T less than Tm, this is negative term, whereas this is positive term, this also we know, and as a result this has to be higher enough to take care of this. This is what we are talking about. So, you can see that from all these arguments we come to one conclusion, that this, it is this to a large extent decides this. Of course, gamma is also very important, but gamma is not in my hands, gamma is not in my hands. Gamma is an interfacial energy between solid and liquid, and once I say define a particular metal that I am solidifying, its gamma is fixed. So, that is not in my hand, but this is in my hand, this delta GV I can change it. So, many people have tried to understand how to calculate this delta GV, and if you want to calculate the delta GV, basically it can be broken into two parts. One is delta H, we will not talk about V anymore now, because whenever we say delta G, it is basically the volume free energy that we are talking, because the moment it is surface we use actually a different term, gamma. So, the moment I say delta G, it is always the volume. Okay. So, if I assume that this is, I can say that this is this. I want to know delta G at a temperature T less than the melting point, this is what I want to know. And if I want to know that, what I need to know? I need to know what is delta H at temperature T, what is delta S at temperature T less than the melting point. If I know these two, I can calculate this. How do I know these two? To know that, that is where we see that delta H at any temperature T can be expressed as an expression in terms of delta HF. Okay. I need to have a reference point. What is the reference point that I know is the melting point? At the melting point I know what is the delta H. Any standard handbook will give you what is the heat of fusion at the melting point, but I do not know what is this heat release between liquid. Whenever I say delta, delta means liquid to solid. In our case it is liquid to solid, some other case it can be some solid to another solid. So, whatever I am talking as is a change of enthalpy when a liquid is changing to solid, that change is what we are talking, and that change at the melting point is known to us. At the melting point it is nothing but delta H of fusion, latent heat of fusion, and if I know that, then I can say it is delta H minus integral delta Cp dt T to Tf. This I can say. So, delta H at any temperature can be found out if I know the delta Cp. Delta Cp, what is the delta Cp? Heat capacity difference between liquid and solid. That means, if I can have an expression of heat capacity in terms of Cp equal to A plus Bt plus C T to the power minus 2, and if I know these ABC constants for both liquid and solid, in principle I can plug that into this and then simply do the integration, get this value, and this is known to us, and I can find out this. Similarly, I can say delta S at T can also be written as delta SF minus integral C delta Cp dt by T T to Tf. Am I right? This appears to be such a easy thing, but in practice it is not easy. Where is the catch here? The catch here is trying to find out when I want delta Cp. What is delta Cp? Delta Cp is Cp of solid minus Cp of liquid. Remember, whenever I say delta, I always write product minus the reactant. The product for us is the solid, the reactant is the liquid. So, Cp of solid minus Cp of liquid, and if I want delta Cp at temperature T less than Tm, I need to know the Cp at the temperature T, Cp of solid at temperature T, Cp of liquid at solid at temperature T, then I can find out delta Cp. Am I right? Now the question that comes is, to find out Cp at temperature T is not very difficult. I have an aluminum, okay. I want to find out the heat capacity of that aluminum at temperature 600 degrees, which is below the melting point. Melting point is 660. Measuring this heat capacity of aluminum solid at 600 degrees is not a problem. I can put it into a DSC and happily measure the heat capacity. But if I want to measure the heat capacity of the liquid at 600 degrees centigrade, how do I measure? I want to know the heat capacity of liquid aluminum at 600 degrees. To know the heat capacity of liquid aluminum at 700 degrees is not a problem for me, no problem, but at 600 liquid does not exist, and if I somehow bring the liquid aluminum to 600 degrees centigrade and start measuring, by the time you measure it may not be liquid, it will become a solid. So, practically it is very difficult to measure the heat capacity of the liquid at temperatures below the melting point. That is why if you have ever seen a handbook such as Smithel's handbook, they give you Cp data in the form of Cp equal to A plus Bt and things like that, and they say that this particular thing, the A, B, C values that they are giving are valid only in this temperature range. They say for a liquid, they say above 660 for aluminum it is valid, below 660 that particular A, B, C are not valid, because nobody has measured them, nobody can measure them unless there is a liquid which can be easily undercooled and still kept as liquid before it actually crystallizes, something like a glass forming liquid, like a silicate glass you can happily undercool. Yes, nano aluminum, no, I am talking of measuring the liquid. Nano aluminum actually melts at lower temperature, is not it? We are not measuring the heat capacity of the solid, we are talking of heat capacity of the liquid. So, but then the question is that for that particular nano aluminum, okay, the melting point you have already crossed. So, you cannot, you see, you cannot compare apples with bananas, okay. So, the moment I say nano aluminum and its melting point, let us say is 600 degrees centigrade, if I say I am measuring the heat capacity at 600 degrees centigrade for the liquid, but that is a stable liquid already, it is not a metastable liquid, it is not an undercooled liquid. Is it an undercooled liquid? And then if you are measuring of that, it is of no use to you, because that is of a different type of material. I am talking of a bulk liquid undercooled to below the melting point, and I am measuring the liquid what is called the Cp below the melting point and maintain that liquid as a liquid during this measurement. And this is possible only when the solidification of the liquid into a crystal is very difficult. That liquid can remain, there are so many polymer liquids which do not want to crystallize easily, all that is why if you go to any modeling fellow for solidification, they all do modeling on polymers. If you have ever read a book on solidification like a Bruce Chalmers, or if you have read a book Malin Sakerka's book or any other books, you will see that all the modeling works that they have done, physical modeling, not really mathematical modeling, physical modeling works are all undercooling experiments. For example, how do I know a material has undercooled? I say that undercooling and microstructure is related. Why? Undercooling and I are related. So, I can actually measure the I. How do I measure the I? I need to be able to see how many nuclei are forming, and if I want to physically see these nuclei forming, I should have something which is a transparent liquid in which actually nuclei are coming. So, people have done a large number of experiments on transparent liquids, which are polymer kind of liquids, sessilonitrate, and there are so many such things where people take such liquids which are more difficult to actually crystallize, and in such liquids one can do this. In a normal metals this is very difficult, you cannot undercool a metallic liquid and then retain it to be liquid, and that is where the problem comes, is measurement of this, and that is where many people started making assumptions. The first fellow to assume something is a person by name Turnbull. Turnbull said, let us assume delta Cp is 0, as there is a crudest assumption one can think of, and we know definitely it is not close to reality, but there are so many things we assume. For example, ideal solution in thermodynamics is not close to reality, but we still assume. So assumptions, one can assume anything that he wants. So he assumed delta Cp is to be 0, that means difference between the heat capacity of solid and liquid is the same. Once you assume that, what happens, this whole these two terms vanish, isn't it? These two are 0, once they are 0 then these terms vanish, then I can say delta H at delta G at any temperature T, at any temperature T is nothing but delta HF minus T into delta SF. Why? Because delta H becomes equal to delta HF, delta S becomes equal to delta SF, am I right? And that is where you see a typical expression that you see in all standard textbooks, where you see that this is equal to, and delta HF SF can always be written as delta SF equal to delta HF by TF, TF only at TF it is valid, isn't it? So because from the basic definition of ds itself, ds equal to dH by T, so if I use that then I can simply say that this is delta HF by T into delta HF by TF, and that brings you to a and that leads you to a formula which is delta SF into delta T. Or to do this simply, you can multiply this and then say that you can convert this into delta SF into TF. You take it as delta SF into TF, take out delta SF common, and you see TF minus T, TF minus T is delta T. So you can now say delta G is this, and this is what all standard textbooks talk about it, but this you would not have known has come from such a easy assumption, such an assumption which is actually not valid. So but this is what all textbooks talk about, but and then after that there are large number of people who have tried to make various assumptions, because measurements are difficult, and after assuming bring out an expression for delta G, and then try to take certain experiments, try to conduct certain experiments on those systems where you can actually undercool the liquid and still measure the Cp of the liquid, which are not definitely metallic systems but other types of systems, and see if that delta G that you have calculated based on that particular formula or derived based on the assumption matches with the actual delta G that is measured. How do you measure the delta G? By measuring the delta Cp. I can get this delta H and I can measure this and I can get the delta S, and once these two can be measured, I can actually measure the find out what is the delta G at any given temperature, and that if it matches with whatever assumptions that we have made. And what are the various assumptions? One assumption where people have said, let us assume delta Cp is not 0 but it is constant, and its value is equal to delta Cp at freezing point. This is one of the assumption made, which is what we call it as Thomson and Spapen.
Sir, is there any problem if I extrapolate the Cp of liquid? If I extrapolate the
Correct. So that is what one possibility could be. If I know how Cp is changing of the liquid, you extrapolate it, that is one way. But the thing is, we for us to know whether the extrapolation is valid or not, you need some experimental, any extrapolation, okay, somewhere you need to have some experimental validity, and the experimental validity is actually coming from not metallic systems, from the non metallic systems. So just because this extrapolation is working in non metallic systems, can I assume that it would work in metallic systems is another thing. So one can always argue, but people are trying to do that. So people are trying to do that, and this is one such assumption, and once you take that this is constant, then again this integration becomes easy for me. I can take the constant out. So and then there are a variety of, if you are interested, there are some recent papers on this. I would get you a reference, a paper by us, we have also done a lot of work on this in Applied Physics Letters 2003, by the first author is K. Mondal. You can see Mondal and Murthy, where we have tried to do certain other ways of doing the same thing. I do not want to go deeper unless you are really serious about it, to find out an expression which would fit for variety of liquids, because most of the assumptions that people have done, each of them have certain limitations. It would fit for binary liquids, but it would not fit for ternary and quaternary, because now we are talking about bulk metallic glasses. Luckily in case of bulk metallic glasses, people are able to do certain experiments, because bulk metallic glasses, one of the advantages is that liquid does not want to crystallize easily, because the TTT curve is shifted to the right to a great extent. That means the nucleation is more difficult in such liquids, because the liquids are viscous. So in such liquids there is a possibility of making measurements, okay. So in such cases people are able to measure and see that whatever long back people, I can tell you, there was the major assumptions. One was by this man Hoffman. If you read this paper you will get all these details. Then Thomson and Spapen I have already given, and Jones and Chadwick. One has said, let us assume the Cp as that Cp where delta H is 0. So Hoffman's assumption is that, so delta Cp is that at delta H goes to 0. In principle this delta H, which is delta Hf minus T integrals delta Cp dt, in principle at some particular temperature the delta H actually goes to 0. It could be a theoretical temperature, the way I have showed you earlier. If you remember this, when you plotted delta Sf or simply S in entropy itself, you remember there is this kind of a thing, and we said if I extrapolate this at some time it intersects that, and at that temperature delta Sf is 0, is not it. Similarly, if I draw H versus temperature, I will again see a similar situation, and that H also if I extrapolate at some stage it would go to 0. And in principle actually if delta Sf goes to 0 and delta G is also 0, automatically at the same temperature delta H also goes to 0, because delta G is finally nothing but delta H minus T into delta S, is not it. So if delta G is 0, delta S is 0, and automatically you will see delta H goes to 0. So there are a lot of theoretical calculations to see whether this and this are exactly the same or not, and to a large extent they come closer to 0. So whereas when Hoffman talked about it, he does not bother about this. He says let us assume that delta Cp and take the delta Cp absolute value of it as that you would get when delta H goes to 0. At that value find out what is the Cp of the liquid, what is the Cp of the solid, and that you can, and in principle one can calculate. If you assume that this is going to 0, then extrapolate H as integral Cp dt, and if you put this as a delta H integral Cp dt, and which is nothing but delta Hf minus integral Cp dt, and take this as 0, and if this is 0, what is this delta Cp where this is 0, okay, and you can get in terms of the expressions of delta Hf. So, you will get some value of delta Cp in terms of delta Hf, and that value you plug it into that particular equation and then try to do it. That is one way of doing. And Jones and Chadwick said let us assume that delta S, the delta Cp is that value where delta Sf goes to 0. This is another assumption, a variety of assumptions. I want you to actually go through because there are lot of derivations. I do not want to really go into these derivations, but for those who are interested, if you read this paper you will know most of them, okay. So, this is one problem that all of us face when we talk about undercooling. So, we do not really know, and to a large extent everybody uses this because it is a very easy expression. And in fact, I should also tell you that in this connection there is a professor by name Professor P. Ramchandra Rao. How many of you have heard of him? Anybody who has heard? Yeah. Who is this man? He was a former vice chancellor of BHU. He is a man who did a lot of work on undercooling, undercooled melts, and he has 2 theories credited to him on the same thing. One, he tried to expand the delta G by a Taylor series expansion. We simply took it as a mathematical expansion, and when you try to expand delta G as a function of Taylor series, then you will get different series order, okay, the first order, second order, third order. At some stage you truncate it and try to calculate the delta G. That is another way. Again, in this paper you will see that also. So, there is again another thing called hole theory. Assume that the liquids are composed of a free volume, that there is always certain holes, as if, because definitely there is much more free volume in a liquid than a solid, because solid has definite crystalline structure, crystalline solids only I am talking about, and there you talk about tetrahedral voids and octahedral voids and things like that, whereas in a liquid you have much bigger voids that we can talk about, and that is what hole theory talks about it. And from that they tried to derive what would be the Cp of a liquid at various temperatures, assuming that these holes kind of change their dimensions as a function of temperature. And so, there are certain theoretical assumptions there again. So, when they tried to do it, they got one expression which is based on that, that is again another expression that is used. So, there are variety of these expressions which are available in the literature, and people depending on what suits a particular system, in all the cases they suit a particular system, but they may not really suit, because that is where each liquid behaves differently, like each of us behave differently. So, each liquid would be different because of its nature, though we can more or less assume that liquids are all similar because their structure is similar. But if I take an iron based liquid and an aluminum based liquid, both of them, though we say it is liquid, this iron when it solidifies it gives you a BCC, aluminum when it solidifies it gives you FCC, is not it. So, that means there must be something different in these two liquids, though we say they both are liquids. That is where you would see the clusters are different in both of them, and based on these clusters its behavior would be different. So, that is how people see that some of these expressions are valid for certain things, in some cases they do not. So, okay, now let us how do we do? Yes, that is another question. Validation, how do we do? Validation is again based on those glass forming. The reason why people bothered about all this to a large extent is after 1959. After 1959, when Paul Dewey showed that it is possible to get a glass from metallic liquids, that is the first time somebody talked about a metallic glass. Till then people knew about glasses, but they are all silicate glasses, that we know a silicate can be easily made into a glass, but a metal can be made into a glass is something which for the first time people have seen in 1959. Then when they are able to make, so people wanted to know what was the undercooling that is necessary for making a liquid into a glass. So that is where a lot of calculations took place to find out what is that delta G, how does it change, the driving force for solidification, how does it change as a function of the temperature. And there they try to always take the glass forming liquids. The advantage of glass forming liquids is, glass forming liquids, the liquid is a stable liquid, it does not want to crystallize easily, that characterizes a glass forming liquid from another liquid. That is why when I said if you take eutectics, we talk about a deep eutectic and a shallow eutectic. In one of the classes I think we talked about it, and in fact we even tried to give how do we measure this depth, okay, in terms of a certain expression. We basically take the melting points of the two metals, consider kind of a linear relation between the two for a particular alloy, and differentiate that temperature, I mean take the difference of that temperature with respect to the eutectic temperature, and we call it as delta TL mixing, something like that. And we said if it is smaller than certain number, if it is a shallow eutectic, if it is greater than a certain number, it is a deep eutectic. And these are more of empirical, because they have seen that wherever this crosses certain number, they saw a glass formation in that particular eutectic. Wherever it is less than a particular number, they did not see a glass formation. So from that people started talking about shallow and deep eutectic, and in all these deep eutectics where glass is easy to form, and in such cases people were able to make those measurements. So when you say how do you validate, okay, people were able to validate in those cases where it is easy to, that means you can undercool the liquid and still this liquid is not able to become a solid crystal, and during that whatever little time that is available, for example if you have heard about what is called microgravity solidification. Interestingly, I would like to tell you, all those who are interested in solidification, November 20th to 23rd here we have an international conference which we are organizing, where all the people who have been working on solidification, who are working on solidification, the top brass people come. It is a conference which we organize once in 3 years and bring everyone who does modeling on solidification, who does experiments on solidification. So that is where you will see a lot of people, the best person who works on glasses is one Professor Inoue, he is coming. So there are a lot of people who come. It is a small conference, about 100 people, 80-90 people, and but it is a very focused conference, everything on solidification, and we have been doing it. This is the 4th conference we are doing, last 10 to 12 years we have been doing this. So what I wanted to tell you is that you will see that all those people who have been doing this undercooling, there is one branch of this undercooling which people call it as solidification under microgravity. When I try to solidify liquids without gravity or at very small gravities, how does this liquid solidify? Whether the microstructure that evolves is going to be same as what you get under gravity or not. We are all compelled to have a gravity on the earth. So whatever microstructure that is coming, we accept it, that this is possibly the type of microstructure, because there is always we are aware of what is called gravity segregation, okay, in most of the alloy solidification, but this segregation is something which we have to accept because gravity is there. So in case there is no gravity, obviously you will not see this gravity segregations take place. Similarly, dendrite growth, dendrite nucleation, is it a function of the gravity? So there are a lot of people who do experiments. There are people who have been doing experiments on ISS, the International Space Station. In fact, Kalpana Chawla, who died, many of you possibly are aware, in one of the space shuttle, they were doing at that time experiment on solidification, and incidentally again this is an experiment designed by another Indian professor, from IIT Kharagpur. There is a professor by name Dhinda who does a lot of work on microgravity solidification. This was an experiment that was going on there. Basically they wanted to see if you take a composite, okay, let us say aluminum silicon carbide composite, you want to know where these silicon carbide particles segregate. Do they go to the grain boundaries of aluminum or they are inside this aluminum? That depends on whether the growing front will push the silicon carbide particles or will it engulf. Okay. Once it engulfs, then you will see it goes inside. This engulfment or pushing, there are a lot of theories that are available. People wanted to prove it in a microgravity, so they are doing experiments on that. So there are a lot of people who do microgravity experiments who will come here and make their presentations, you will see them. So what is important there again is how does various forces influence the solidification. We have been only talking about only temperature as one of the force, we even do not consider pressure at all. So the moment you bring in the pressure aspect, how does it influence. So this is pressure can be just a vacuum, you can talk about it, and the other thing that we can think of how the microgravity brings in pressure, that is another area, lot of people are interested in that. So the point that I want to make here is that many people who are interested in undercooled liquids, whether this undercooling is achieved because of microgravity, because when you do it under gravity, many people have observed the liquid does not become a solid immediately at the melting point, but it undercools and then becomes a liquid solid. So and they were able to see that this extent of undercooling is a function of the extent of microgravity that you provide, but in a normal earth it is very difficult to provide a microgravity, excepting under cases where people have designed. For example, in Germany there is a what is called a drop tower. You take a liquid droplet and from 100 feet you drop that liquid droplet. Let us say a furnace, a small furnace, you keep it, liquid is metal is liquefied, and this liquid through an orifice it comes out and then simply falls in a drop tower, which is evacuated and kept in high vacuum, so that there is no oxidation and things like that. And such liquids, when they took after it solidified, took that solid piece and then tried to solid, when I say solid piece, it is just like a flake, because what you are dropping is 1 millimeter droplet possibly, and they have seen that from the microstructure it is all indirect. You see the microstructure, and from the refinement that you have seen in the microstructure, you quantify what could have been the nucleation rate, and from the nucleation rate back calculate what would have been the delta GV, and from the delta GV again back calculate and say this could be the undercooling. So this is how people go, because there is no way directly for you to measure the undercooling, excepting if there is a way that it is a transparent liquid that I am undercooling, and I can see with a video, very fast video, that as I undercool I can, for example, Professor Fani Kumar does experiments on levitation. If I can levitate a liquid and then there are no surfaces available now, this liquid is now being allowed to solidify, and I keep on reducing the temperature and then catch up if it can show where the nucleation is coming. And in a normal metallic material they are all opaque, so I cannot really see if the nucleus is coming inside the liquid somewhere at some particular temperature. Catching that temperature is not very easy, but in other organic liquids where there is a possibility of undercooling, people have done these experiments and to see where exactly what is the temperature at which the nucleus solidification. Of course again the problem is nucleus is very small, of the order of few nanometers. How do I catch that? Because my camera may not have that resolution. Obviously it is a optical camera, it would not have a resolution of an electron microscope, so it has to grow to a few micron size for you to be able to actually catch it. So these limitations are there. Within these limitations there are a lot of people who are trying to do those and find out that temperature where they have seen the first solid and back calculate that if this is my resolution of let us say 10 microns or so, and for if it I visualize it at this particular temperature, at what temperature it would have nucleated. again with certain assumptions one can back calculate it. So, all these there are a lot of people, I mean it is a wonderful field solidification, a lot of people are working on it. So, again all of them are driven by this simple thing, that how do I actually predict before even doing the experiment, can I predict that if I cool this liquid at this rate, this will be the grain size that I will get, is not it. That is what everybody wants to know, that can I predict the grain size that I get, or a microstructural refinement that I can get, and or what should be the cooling rate that I should use to get a glass in this particular liquid. So, for all this you need to have an the models that are available, where you have a relation between the cooling rate and the undercooling. Cooling rate and undercooling to some extent we can understand. Okay. So, a relation between cooling rate, undercooling and the delta G, so that delta G to I, again the relations are more or less clear to us. Delta G to I relations are clear, but the delta T to delta G relations need to be established, and that is where all this modeling has been happening. And if you are interested, I can give you a large number of papers, but anyway we will close that discussion at that. There is another aspect which I thought I will tell you, again because we are talking of again nucleation, we started it, but we did not grow to a large extent on that earlier. What is the shape of the nucleus? You asked me this question some time back. What should be the shape of? We always easily assume sphere, okay, and we talk about 4/3 pi r cube, 4 pi r square gamma, all that. So, what is the shape of the? So, I was telling you that each plane in a crystal, because when I say a solid, I am not talking of a glass here, I am talking of a crystalline solid that is coming out of a liquid, and if it is a crystalline solid that is coming out of a liquid, it has unit cells, it has planes, and different planes have different surface energies. If different planes have different surface energies, then and how do I assume that a liquid will have a spherical particle? Because the moment I say spherical, what kind of a crystal structure that I can imagine which would give me a spherical particle? Because basically what is a nucleus? Nucleus is nothing but a bunch of unit cells, is not it? There are a number of unit cells. So, that means I take a unit cell, I extend this unit cell with a number of other bricks, it is like a wall with a number of bricks in all the 3 dimensions, that becomes a nucleus. And if I take a brick with certain shape, we have 7 shapes that are known to us, which are crystal systems, and 14 Bravais lattices. Out of these 14 Bravais lattices, I choose any one of the Bravais lattices, and that unit cell I add a number of those bricks in all the 3 directions. Can I ever get a sphere out of it? It is not possible. It is not possible that I can think of a nucleus which is composed of unit cells, and the unit cells, none of the unit cell is a sphere. If the unit cells are not spheres, then obviously this nucleus cannot be a sphere. Then what should be then the shape of it? Then what people said is, now let us assume that the unit cell, the nucleus is composed of certain planes. The moment you think of the outside planes, at this moment we are thinking that it is a sphere, it is a curved. It is not possible that atomic planes are curved, atomic planes are not curved. So, as a result, a actual nucleus would be something like this, with certain planes on the outer surfaces. In a 2D it is like this, in a 3D it will have other faces. Now, if that is the case, then the actual shape of the nucleus is that which minimizes the overall surface energy. It chooses those planes for its enclosure in such a way that the overall surface energy is minimized. For that, Wolf, there is a Gibbs plot, people talk it, Gibbs long back talked about it, what people call it as Gibbs plot. What he has done is, let us assume a crystal structure, let us say cubic, let us say FCC aluminum is solidifying, liquid aluminum is solidifying into FCC aluminum. What should be the shape of the nucleus for the FCC aluminum that is coming out? if I want to know, let us simply think that every plane has a certain surface energy. There is a gamma of 111 plane, there is a gamma of 110 plane, there is a gamma of 1100 and so on, am I right? And this surface energy depends on what? It depends on the number of broken bonds, and one can easily calculate this in principle. And so these surface energies are there, and if I try to find out a polar plot where if I take a dot and then draw a direction and call this as 100, a perpendicular direction I call this as 010, and this is 001, let us say, and I say in this this direction I know these values, let us say gammas, and in each direction the length of this particular vector I take it as a scaling of one of the surface energy, let us say. And so let us say if I take a vector like this, that means this represents gamma of 100, let us say, and this is gamma of 010. That means every surface energy, for every surface I show it in the form of a vectors, and then once I show that, I can talk about gamma of this. If this is 100 and if this is 0 bar 10, this will be 1 bar 10, am I right? And this will be 110, and the value of this gamma, if I take any scaling factor, and once I take the scaling factor I can talk about this is the value, and once I put all those vectors, then what you do is you simply draw perpendicular to those vectors, and this perpendicular now represents that plane. Any vector for a particular plane perpendicular to that is actually that particular plane. If I, for example, if I draw a perpendicular surface like this, okay, that surface actually is a 100 surface, and similarly if I draw a surface here, I can think of that as a surface of 110 surface. Now what you do is there can be some plane which could be, if this is 110, this could be 210, and its surface energy is so high, let us say that this vector goes out to a large extent, and now I draw a perpendicular to that also, and for each of these vectors you draw perpendiculars. In a 2D we are doing, in a 3D basically you are drawing surfaces which are perpendicular to that, and if you do this, find out that particular enclosure which has the minimum area in a 2D, in a 3D the minimum volume, that will be minimization of the surface energy for that particular structure. If I know for a particular structure, for a particular, and this gamma of 111 for an FCC will be different from gamma of 111 for a BCC. For a given structure I need to calculate these values, because 111 plane in an FCC is different from 111 plane in a BCC, their packing factors are different. So as a result, for a given structure, if I can calculate these things and do this and then find out a particular shape which gets formed, which has the minimum area, is the one that actually has, the moment a plane, one of the plane, the vector is going out, that means it has a large surface energy. I am avoiding all those large surface energies and taking only that particular area, that is the system would choose that particular shape in such a way that it need to spend minimum energy, because surface energy is something which you need to spend, and where from you are spending, it is from the delta GV that is available. So it would like to spend the minimum energy before it actually solidifies into a shape. So, it would choose that particular shape. This is what is called Gibbs plot, which is what has been used to find out for various, and people have done this kind of calculations to find out what should be the, that is what people talk about tetrachoid ecahedron is the shape that comes out, and variety of names are given to such shapes depending on which structure that I am. If I say BCC, I can actually in principle calculate what should be, but will that remain after it grows is another question. The point is, once it grows, the shape could be different. Why? Now, if I take this particular shape, I will continue a few more minutes. When it grows, the rate at which this plane grows and the rate at which this plane grows is different. Why? Because the packing density of this plane is different from packing density of this plane. Whenever this has to grow, the rate at which it grows depends on how many atoms this plane needs to fill up that plane. When that plane is filled, it grows by a small delta x. So, if a 110 plane needs less number of atoms than 100 plane, 110 plane will move faster than 100. The plane which is a loose packed plane will always move faster than the plane which is close packed, and as a result, after some time you may see that this, if it is not growing faster, if this is growing faster and these 4 are growing faster, okay, slowly you will see that the final shape later after the growth, you will see the shape would have changed, these planes will not exist there. So, you will see a different. So, the nucleus shape is possibly is why possibly I should say, it is definitely different from the shape after grown, but the problem is we can only see the shape after it has actually grown. We will not be able to see the shape of the nucleus unless you freeze the nuclei somehow and put it into an electron microscope and be able to see it. So, that is another problem with all these calculations. Though we are able to calculate what is the shape of the nucleus, we do not know whether this is going to remain, and the actual shape that I am seeing is a growth, okay, shape modified by the growth. That is the reason why you will always see, for example, in aluminum silicon alloy you see silicon needles. In a iron carbon alloy, the cementite is like a blocky particles, chunky particles. Why does this happen? Because certain directions have a faster growth rate in a silicon, so it grows faster there. So, this is another issue that one need to consider, but for the sake of academics one can calculate the shapes like this. That is why this you do not see in every textbook this information, because this has its own limitation, because this shape that it can predict, you may not be able to actually seeing this shape after it has grown. So, it has obviously certain limitations. Okay, we will stop.